Good morning. Myself Dr. T. Jagdish, working as Assistant Professor 3 in the Department of Electronics and Communication Engineering. Now we are going to see a topic on electromagnetics, which is Ampere Circuital Law. This Ampere Circuital Law states that the magnetic field intensity around a closed surface can be calculated by determining the current enclosed by the surface. So this is the statement given in Ampere Circuital Law. I'll repeat once again. The magnetic field intensity around a closed surface is equal to the current enclosed by the closed surface. So this statement was given by Ampere. So this is Ampere Circuital Law. The major limitation of this Ampere Circuital Law is it can be applicable to symmetrical and closed surface. So we can apply Ampere Circuital Law only to symmetrical and closed surface. So now let us use this Ampere Circuital Law and determine the magnetic field intensity of a long straight conductor. So for this, let us take a cylindrical coordinate system where we have a long straight conductor and the orientation is along a phi direction, that is a vector phi direction. So let us consider this a long straight conductor. Now we will evaluate the magnetic field intensity of straight conductor using Ampere Circuital Law. So we know the statement Ampere Circuital Law states H vector dot dl is equal to I. So we have taken the orientation along phi direction, hence in a cylindrical coordinate system my differential length on phi direction is given by r d phi a vector phi. Similarly, my magnetic field intensity along phi direction can be calculated using this concept into r d phi. So this can be evaluated by integral of h phi r d phi over the limit. Since it is a line integral, the limit for phi varies from 0 to 2 pi. For a cylindrical coordinate system, the value of phi ranges from 0 to 2 pi. So if I integrate with respect to phi, so I'll get h phi r as a constant, integration of d phi is phi. So the limit is 0 to 2 pi. So if I substitute, I'll get 2 pi r into h phi. So this is my left hand side. So what we could see is my magnetic field intensity along phi direction into 2 pi r is equal to I, the current enclosed by the closed surface. So from this we can identify or we can determine the magnetic field intensity of a closed long straight conductor is I divided by 2 pi r ampere per meter. So the unit of magnetic field intensity is ampere per meter. So the magnetic field intensity of a long straight conductor along phi direction in a cylindrical coordinate system is calculated by h phi is equal to I divided by 2 pi r, where r is the length of the conductor. So this is a simple application using Ampere Circuital Law to determine the magnetic field intensity of a long straight conductor. Now we will see one problem based on this. Let us find the flux passing through the plane where your plane is along phi is equal to, it is a cylindrical coordinate system where your phi is pi by 4 and the radius of the cylinder lies between 0.01 to 0.05 meter, and the z-axis is between 0 to 2 meter. A current filament of 2.5 ampere is along A vector z direction. A vector z direction in free space. So this is my question. So you need to find the passing through a plane surface which is a cylindrical surface. So it is a cylindrical surface and you need to find the flux passing through the surface. So the question is, you need to find the total flux passing through the surface. So to determine the total flux passing through the surface, so first we need to identify the magnetic intensity H vector. So this is the first component you need to identify. So we need to identify what is my field intensity, and from the magnetic field intensity we have to determine what is my magnetic flux density. From magnetic flux density you can determine the total flux passing through your closed surface. So first let us evaluate the magnetic field intensity. So you need to find H vector. So from the given problem we could see it is a long straight conductor. So my magnetic field intensity of a long straight conductor, just now we have seen the derivation. So H vector is equal to I divided by 2 pi r into A vector phi. So this is the formula to determine the magnetic field intensity of a long straight conductor. So we know the current passing through this is 2.5 ampere, it is given in the problem, divided by 2 pi r. So we don't know the r value, it is given in the form of range from 0.01 to 0.05 meter. So just substitute r as it is into A vector phi. So if I simplify this, my answer will be 0.3978 by r A vector phi. So this is my H vector. So we know the relationship between and magnetic flux density, B is equal to mu into H vector. So what is mu? Mu is my permeability, where mu is mu naught mu r. Mu naught is absolute permeability and mu r is relative permeability. So if you look at the problem given, the statement given is in a free space. So for a free space my relative permeability will be 1. So mu r is 1. So we know the value of mu naught. Mu naught is 4 pi into 10 power minus 7. So just substitute these things. If I substitute, my B vector will be, so my B vector will be 4 pi into 10 power minus 7 divided by r into 0.3978 A vector phi. So this is my B vector, which gives you, if I simplify, I will get 5 into 10 power minus 7 by r A vector phi. So this is my magnetic flux density. Now we will calculate the magnetic, that is the total flux passing through the given plane, that is phi. So the formula to calculate the total flux, which is surface integral of your magnetic flux density enclosed in a closed surface. So it is a surface integral of d vector dot ds. So as we have already given in the question, the orientation is along phi direction. So my surface area ds is calculated by dr dz into a vector phi. So this is my surface area. So if I substitute this, since it is a surface integral, so this becomes, what is my b vector? 5 into 10 power minus 7 by r a vector phi dot product of r dz a vector phi. So if I simplify, so my integration is 0 to 2 along z-axis and 0.01 to 0.05 along r-axis, 5 into 10 power minus 7 by r into dr dz. So now I need to integrate this. So if I integrate this, what you will get is, so 5 into 10 power minus 7 is a constant. So integration of 1 by r is ln r. So we know integration of 1 by r is ln r, and integration of dz is z. If I substitute and simplify, the total flux will be 1.609 Weber. So this is my total flux passing through the given. So by this simple problem, we could understand the Ampere Circuital Law and how to determine the magnetic field intensity of a long straight conductor using Ampere Circuital. Thank you so much. Thank you for listening.